hello there. We are going to do our second to the last section in chapter 11 today, which is on ratio of areas. But if you see here, I have a little note for us that is saying that we are going to have an assessment on chapter 11 at the beginning of next week. Now, I'm still working out what that assessment exactly is going to look like, what format it will be in, but we're heading that direction. I want to see where you're at. So expect some review materials as we get going this week, and then I will update you the format that looks like. So we've got 2 more sections. Let's go ahead and get started. Today's section is about some trends that we find in ratios of areas. So if you look here, this DOT, that stands for the daily learning target. It says we can compare areas and find patterns to help us solve problems. So today will be about noticing patterns that come up as we try to get some general rules to work with. So here is the first scenario. So what we're going to find is this first ratio comparison that we're going to look at is the figures that have the same base or they have the same height. So the first thing I've asked us to do here is there are 3 triangles shown in the diagram below. There's triangle ABC, there's triangle ACD, and there's triangle BCD. All right, now we're going to draw the height of all 3 of these triangles. And so then now if we look, I'm going to use some highlighting here to color code this. So if I start with triangle BCD and I draw the height from vertex C, that is going to be, drop a line straight down, that will be this segment right about here. Awesome. Okay, let's move on. Maybe we'll do the biggest triangle in pink. So triangle ACD. Well, if I start from C and I try to draw the height straight down to the base, ignoring everything else, well, look what just happened. The height ends up being the same segment as the height of the first triangle that we drew. And just to convince us, let's do the last one here. Let's use blue. For triangle ABC, if we try to draw the height again from its vertex, that is the same height as all 3 segments we've drawn before. So these 3 triangles, although they're different size, they all have the same height. So this looks complicated. So now you can move it aside or you can leave it. The notes have it shown. So the thing that we've noticed as we work this through is that all 3 triangles have the same height. The problem didn't tell us what that height was, but we know that it's the same. So now I'm going to draw this universal height, draw it at a right angle, and let's say that we call it height h, like we're used to. Don't know how long it is, but we know that it has height h. So now, if we look to problem 1, it asks us to find the ratio, that's what our division sign means, of the area of triangle ABC to the area of triangle BCD. So what we're going to do is for triangle ABC, remember that the area formula is 1/2 base times height. Well, let's locate its base. Its base is the segment AB of length 3, and the height is h. So that would make the area of 1/2 of 3 times our common height of h. Then for triangle BCD, that is the triangle on the right, the smaller one, its base is 5, and so its area would be 1/2 of 5 times the height of h. And we're using something that we don't know, but we're going to see what happens as we do that. So we're just asked to find a ratio. A ratio is a fraction in simplest form. So now I have a fraction. I just want to reduce it. Do you notice anything that cancels? If we were together, my hope would be that people noticed that the 1/2s cancel, the h's cancel, and what does that leave us with? That leaves us with 3 over 5. So that means that the ratio of the area of triangle ABC to BCD is 3 to 5. And where do those numbers show up in the problem? Those show up as the bases. So it ended up being that the ratio of our areas, because it had a common height, was just the ratio of the bases. So using that idea here, let's set it up again. The next ratio asks us to find the area of triangle ABC to ACD. So take a pause. What is triangle ACD? Oh, that's the largest triangle. Well, the problem didn't tell us how long its base is, but remember we can add those two segments together to figure out that its base has a length of 8, our second ratio. Now that we know that the base of the largest triangle is 8, we can set up a ratio that ABC is 1/2 the base of 3 times h, and our largest triangle is 1/2 a base of 8 times our height h. And then again, if we follow this now where we cancel what we can, the 1/2s are gone. We have 1 on both top and bottom. The h's are gone. And that leaves us with 3 over 8. And here's what happened. We just saw two examples that confirmed what we kind of thought after the first example, is that when we have a common height, there's a pattern happening here that the ratio of the areas of the triangles is the ratio of the bases. And so we can use this rule here to help us compare other ratios as we notice commonality. That was kind of messy. The ratio of the bases. Okay, awesome. So that's the first thing that we found here. Common height means that we compare the ratio of whatever is not in common, which would be the bases. Next up, this problem here is in a similar vein. We have some triangles here. It says AM is a median of triangle ABC. Remember that a median bisects the side to which it's drawn. So that means segment BM and MC are congruent. It asks us to find the ratio of triangle ABM. So make sure we know our triangles, this one, to triangle AMC. So first thing we want to ask ourselves is, if we were going to find the ratio of the areas, if we didn't have a pattern, the most direct thing we would do is use the numbers we have, find the area by hand of each triangle, set them in a fraction, and reduce that fraction. But we don't have any numbers here. They didn't tell us a single value. So does this match with what we found before? Well, both of those triangles have vertex A. And if I were to draw in the height, again, we have that common shared height scenario. So what did we just find from above? A common height means that the ratio of the triangles is the ratio of the triangle's bases. So here's what we know. We don't have any numerical value given for these bases, but we do know that they are congruent. So you have two options. You could, if it's easier for you to think in terms of numbers, let's pick a random number. Let's say that this was BM was 4 units long. That means MC is also 4 units long. So that means that the area of triangle ABM, the ratio of that, which we can do in these colons, or we can do it in a fraction, whatever we're more comfortable with, to the area of triangle ACM is equal to the ratio of those bases, which would be 4 to 4. But you want to reduce those numbers if you can. Well, those reduce down to 1 to 1, which means those triangles have an exactly equal area. Because the bases are equal and the heights are equal, they actually are going to have the same area. So anytime we have a median of a triangle, the median, this is actually an interesting conclusion, the median divides the bigger triangle into two triangles of equal area. Doesn't happen with all of our other segments, but it happens here, which is pretty cool. All right, let's move on to the next type of ratios. Here is a flashback that we found when we talked about similar triangles. If two triangles are similar, then the ratio of their corresponding sides is also going to equal the ratio of corresponding altitudes, medians, angle bisectors, perimeters, etc. So any of the special segments from triangles, if the triangles are similar, the special segments will have the same ratio across our triangles. So we're going to see how that affects us finding the area of two similar triangles. So here, this setup asks us to find the area of triangle EFG and EJK. Looking here, can we confirm these triangles are similar? That is the first thing that we want to ask. Well, we have a shared angle up at E, and then because we have parallel lines, we have congruent corresponding angles on either side of the triangle. So definitely these triangles are similar. And then what is the ratio of corresponding sides? Well, remember here, we want to do the entire side of the triangle. So one of the sides is 4, EF, but for our other larger triangle, it's the full side, add them together. So that makes our ratio of corresponding sides equal to 4/7. So our ratio of corresponding sides is 4:7, and that's going to become important here in a second. All right, so now area. We don't know the base of this triangle. We don't know the height of this triangle. We don't know anything about any of the other sides, so we're a little bit stuck. So we're going to do some manipulation here to prove something. So here's what we're going to do. I'm going to say that for our upper triangle, the area is going to be 1/2 of B1 times H1. I'm going to call that triangle 1 and say that its area, I'm going to change it to orange, that its area is 1/2 of its base, which we're going to call B1, times its height. We don't know what they are, but that's okay. For triangle 2, which is EKJ, we're going to say its area is 1/2 base 2, its base, times its height, H2. Remembering B2 would be, you could say maybe it's this, H2 would be this, so on and so forth. So then doing a little bit of simplifying here, I'm just going to do some rearranging. I can cancel the 1/2s. Those are the same. And then I'm going to write this as B1 over B2 times H1 over H2. Here is what's important. What this symbol means for us here, B1 over B2 means it's the ratio of the bases times the ratio of the heights. Going back up to our theorem, the ratio of our corresponding sides is equal to the ratio of bases, altitudes, medians, so on and so forth. So here's what that means for us. The ratio of base 1 to base 2 is going to be equal to the ratio of our sides, which is 4/7. Alternately, the ratio of our heights will also be the ratio of our corresponding sides, which will also be 4/7. So continuing our problem, that means we can replace B1 over B2 with 4/7 and H1 over H2 with 4/7. And now we can finally multiply those. That gives us 16 over 49, giving us a ratio of areas of 16 over 49. And ta-da, we just solved it without knowing what any of those bases were. There's a relationship here between 16 and 49. Those happen to both be the squares of the numbers in the numerator and denominator of our original ratio of corresponding sides. That will be important here in just a second. All right, so next up, two similar figures have ratios of corresponding sides of 4 and 6. What is the ratio of their areas? So we could work through and we could do this whole derivation that we did before, but what we found is that really by the end, it became the ratio of the bases, which was the same as the ratio of the corresponding sides, which was 4:6, times the ratio of the heights, which was also 4:6. Now, one thing to notice, those fractions could and can and should be reduced. We could do it at the beginning of the problem or at the end. I'm already going, so let's finish it and reduce later. So that becomes 16 over 36, which we need to reduce. Those are both divisible by 4, so that would make this 4/9. So our triangles have a ratio of 4:9. Remember, this is not the exact area, but we could use this ratio to figure out the exact area of our triangles as we go. So this leads us to an all-important theorem, and then we're going to look at some problems here. Here's our theorem. It only works for similar triangles. But if triangles are similar, the ratio of their areas is equal to the square of the ratio of corresponding segments. So the area of some, if we call the one triangle, triangle 1, the other similar triangle, triangle 2, the area of triangle 1 to the area of triangle 2 is equal to side 1 over side 2, so the ratio of corresponding sides squared. And when you square a fraction, you square the top number and you square the bottom. And that's our rule. All right, so let's look at a couple of examples. As you understand this note section is probably going to be one of the longest ones in our unit. As you feel like you're understanding what we're doing, then you can go on to the practice set if you want to pause and take a break and then work on the practice and then come back and look through some of these examples if you get stuck. That's a couple of ways to think about breaking it down because I recognize this is a longer section. All right, here we go. So looking at this diagram, first, let's go to the left side. It asks us to find the area of triangle IML to triangle ISE. Okay, where are those? IML is this little one. ISE is the biggest one. Do those triangles have shared base, shared height? I don't think so. They're different size, but they are similar. We've got those parallel lines, which gives us similar triangles. So then what is the ratio of the corresponding sides? Oh, looking here, I have this bottom base and this other base, which is 5 to 8. So that means that the ratio of those two similar triangles is my ratio of corresponding sides, which is 5 over 8, all squared. And that gives us 25 over 64. Awesome. Okay. Hopefully that should sit pretty well. We found our side ratio, we squared it. Now the next part I do want you to stick with me here because it does play a little bit of mind game. So here's what we want to think about. This total big triangle takes up a ratio of 64 units of space. It might be bigger, some common multiplier, but it's going to be 64 times something. The inner triangle, IML, takes up 25 units times some common scaled factor. So when we go down to the next problem, it asks us to compare the area of SMLE, which is a trapezoid, to the area of the biggest triangle. So if we think about this idea of part minus whole, we can still apply that to ratios. If the whole triangle takes up a ratio of 64 units, and then the inner triangle of 25, well, what's left over from 64 minus 25 would be the leftover space inside for this trapezoid, and 64 minus 25 gives us 40, it gives us 39, and then over the whole thing of 64. So it does come out to be this leftover space inside. If we think about percentages, if this is 25 parts out of 64 total parts, this is 39 parts out of 64 total parts. If we were to add these together, this should equal 1, which is the same as 100% of area is accounted for. So hopefully that explanation made sense of this. So now we can use 39 as the numerical representation of the trapezoid. So for IML to SMLE, that would make this come out to be 25 over 39. All right, let's look at a couple more before we finish. So for number 1 here, it says find the ratio of the area of region 1 to region 2. Before you start, we've really seen two types of problems. Either they're similar triangles or they have some shared segment, a base, a height, from there. So here, can I confirm these triangles are similar? So I want you to stop and I want you to try to find the angles. If you want to pause it and think about it, I'd encourage you to do that. If not, here we go. So we have vertical angles. And then you want to think about, I don't have any parallel lines anywhere, so I don't have that. But what I do have is, if you remember, because it's in a circle, this angle opens up onto this arc. What other angle opens up onto that arc? That's this angle. And so that means that these two angles are congruent because they share the same arc. So this is how our triangles are similar. So for corresponding sides, that means that 5 and 7 are along the corresponding sides. So that means that the ratio of triangle 1 to triangle 2 is 5 over 7 squared, which gives us 25 over 49. All right, that's number 1. For number 2, this is our median situation. Our two segments at the bottom are congruent, and they have a shared height. And when this was the case, we found that the area of triangle 1 to the area of triangle 2, because that was all the same, it came out to be 1 to 1. So again, those sections have equal area. All right, next up. For number 3 here, again, it looks like we might have some similar triangles. The important part is how are they similar? I have my side length of 10, and I want to know which, if the 10 is corresponding with the 3 or the 7. That's going to drastically change our answer. So with this, we have vertical angles, but this time we don't have special circle and right angles, but we do have alternate interior angles, which means following the markings that the 10, the triangles are like flipped around, corresponds with the 7. So that means the area of triangle 1 to the area of triangle 2 is equal to 100, we square them, over 49. Now, one important thing to remember about fractions, because these are perfect squares, they feel like they should reduce. This feels like it's a fraction that reduces, but we only reduce multiplied factors. So we can't reduce anything that squares it. So square rooting the top and bottom of a fraction doesn't keep it balanced. So this doesn't equal 10 over 7. If you put that in your calculator, they're not going to be the same fraction. Those are not equal. We can only reduce like if there's a multiple of 2 in both the top and bottom, or a multiple of 7 in both the top and bottom. So they don't have any common multiples. So keep that in mind here. Okay, for this last section here, I want you to work this problem out if you feel like you're still having difficulty. It's a really good problem just to get you thinking. We have a square garden, 3 meters on a side. How long would I have to make the sides to get this garden to have double the area? This is a trickster, so I want you to think about how that might come out. And then if you look at the notes key, it has the solution worked all the way through. And I'm about to just give you the end answer. So if you want to pause it, work it through, and then restart the video, here is the answer. The answer to this problem is that the side length comes out to be 3 root 2 meters in order for it to be doubled. Go ahead and figure out why that is. All right, that's the end of the notes. Go ahead on to the practice set, and I will see you tomorrow for 11.8.